serving a global membership of nearly 100,000 computing professionals and students. My name is Milind Kulkarni. Currently, I'm an associate professor in the School of Electrical and Computer Engineering at Purdue University. My research focuses on developing languages, compilers, and systems that can efficiently and effectively exploit locality and parallelism in complex applications on complex computation platforms. I'm a member of the ACM and a senior member of the IEEE. And for more on my background, you can see the bio widget on your screen. For those of you who may be unfamiliar with ACM or what it has to offer, here's more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. And you can see some of those highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides, among other things, timely computing information published by ACM, including communications of the ACM and Q magazines, access to the ACM Digital Library, the world's most comprehensive database of computing literature, international conferences that draw leading experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards, and the updated ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you'll find some additional widgets and resources. If you're experiencing problems with the slides or audio, press the F5 key in Windows, Command R if you're on a Mac, or refresh your browser on a mobile device. Or you can close and relaunch the presentation. To control volume, adjust the master volume on your computer. And if you have questions during this talk, please type them into the Q&A box at any time and click the Submit button. I'll organize the questions as Emery speaks, and he'll reserve some time at the end of the presentation to address them. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. And you can check learning.acm.org for updates on this and other upcoming webcasts. Finally, at the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill it out to help us improve our tech talks. And you may also open the link to the survey at any time from the resources window. You can use the Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions to us using the hashtag ACM. We'll be watching for your tweets. And we also have a community discourse page to continue the discussion after this webcast, including questions we won't be able to get through during the Q&A session. Today's presentation is Performance Really Matters by Emery Berger. Emery Berger is a professor in the College of Information and Computer Sciences at the University of Massachusetts Amherst, the flagship campus of the UMass system. He's been a visiting scientist at Microsoft Research and at the Universitat Politècnica de Catalunya, Barcelona, and the Barcelona Supercomputing Center. His research spans programming languages, runtime systems, and operating systems, with a particular focus on systems that transparently improve reliability, security, and performance. He and his collaborators have created a number of influential software systems, including Horde, a fast and scalable memory manager that accelerates multi-threaded applications, used by companies including British Telecom, Cisco, Credit Suisse, Reuters, the Royal Bank of Canada, SAP, and Tata, and on which the Mac OS X memory manager is based. He's also created DieHard, an error-avoiding memory manager that directly influenced the design of the Windows 7 fault-tolerant heap, and DieHarder, a secure memory management that was an inspiration for hardening changes made to the Windows 8 heap. Emery's numerous honors include a Microsoft Research Fellowship, an NSF Career Award, a Lilly Teaching Fellowship, and several awards from top conferences such as PLDI, UPSLA, ASPLOS, FAST, and SLSP. He was named an ACM Fellow in 2019 and is currently serving as an elected member of the SIGPlan Executive Committee. He served for a decade as associate editor of the ACM Transactions on Programming Languages and Systems, was program chair for PLDI 2016, and is co-program chair of ASPLOS 2021. Emery, without further ado, take it away.
All right, thank you so much, Milind. So let me go ahead and do the screen share. Get a little inception going. Hopefully this is actually working. Yes. Okay. Great. All right. So I'm happy to be here today to talk about why performance really matters. So before I do, I'm going to talk about our favorite family, The Simpsons. And so hopefully most of you are familiar with this family. This show has been on the air for an incredible amount of time. But things have changed in this incredible amount of time. So this is The Simpsons today, but The Simpsons actually premiered in the 80s. And in the 80s, they looked really different. I would say they've improved substantially over the years. And this sort of evolution turns out to have been echoed not only in The Simpsons, but also in our computers. If you have a smartphone today, that smartphone today may have 6 cores, each running over 2 gigahertz, 64-bit processor, 4 gigs or more of RAM. You compare this to the world in the 80s, we had computers that were vastly less advanced. Where it was the speed is measured in megahertz, the processors were 16-bit at best, sometimes even 8-bit, and the amount of RAM was much smaller. In fact, if you divide these out, if you put one on top of the other, you can see, roughly speaking, that today's computers are about 3,000 times larger, faster, better than computers in the past. So before the 80s, when computers were so slow, basically, programmers had to resort to languages that were designed to have as little overhead as possible and to be as close to the metal as imaginable. So these robots are meant to represent these various programming languages, starting with assembler, moving into Fortran and C and C++. And I like to call these the metal languages. These languages, by design, have virtually no overhead. And that was really important because computers were just so slow. However, in the intervening years, we've been on this performance ride. So starting around the late 70s and early 80s, computers started getting faster and faster. And so what happened was we had these twin trends that were occurring. One, the number of transistors was going up at a rate of roughly twice every 18 months, known as Moore's Law. I draw your attention to the fact that this is a log scale. So it looks like it's linear, but it's really, really super linear. It's going up by exponentially. And at the same time, clock speeds were going up. And so what happened was these chips were getting more and more gates on them, more and more transistors, and they were getting faster and faster. And so the effect was every year, you could literally go and buy a new computer, and your computer would just run faster. So what the implication was that these metal languages maybe were no longer necessary because computers were getting faster and faster, and we could afford to be a little more slack with how we built these languages. And so in the 80s and the 90s, there was this period of time where a bunch of other languages came out that were vastly less efficient than C or C++, starting with Perl and including languages like Tcl/Tk, PHP, Ruby, and Python. And I like to call these the irrational exuberance languages. These were languages where people simply thought things were just going to get faster and faster forever. And so it was OK to have pretty substantial inefficiencies. So I'm going to focus today on Python when I'm talking about these, but all of these languages share very similar features. So the arrow is pointing to Homer's stomach, and that's because all of these languages are kind of bloated in terms of the amount of space they consume. So you might think that an int, for example, is a relatively small amount of information. It's a small number of bytes. And in C++, the size of an int is going to be 4. However, in Python, that same int is actually 24 bytes. So it's 6 times larger than it needs to be. This is true for it's just true across the board. So it's not just numbers. So an empty list in C++ would be 24 bytes. And in Python, it turns out it's 56, so more than double. And then my favorite example is an empty dict, that is to say an associative array or a map. The size of it in C++ is 24 bytes. In Python, today it's 64, so it's nearly 3 times as much. But this is the result of Python putting on a little bit of a diet. Up until just a year or so ago, it was 240 bytes, so it's 10 times more memory. And I note this is suspiciously close to Homer Simpson's own weight. So definitely Python and these other languages are inefficient in terms of memory consumption, but they're also famously inefficient in terms of performance. So they're infamous that they're slow. And so just to give you a sense of how slow they can be, here is a sample bit of code that does matrix-matrix multiply. So this is the naive matrix-matrix multiply just expressed in a loop in Python. And I want to thank Charles Leiserson for this example. Here is a graph showing the difference in applying different sort of techniques to this Python code. I'm sorry, to matrix multiply. So if Python is 1, C, just writing it in C is 47 times faster. And when you apply all the optimizations that you can do in C and that are included in standard C libraries, it's over 60,000 times faster. So this is a pretty big gap. And maybe it seemed to make sense when Python was going to get faster by virtue of the fact that we were on this ride, and this ride seemed like it was going on forever. But unfortunately, the ride did not go on forever, and in fact has stopped. So we were here, but now we're here. The ride is over. So starting at around 2010, the ride just ended. And what happened was this trend that we hoped and expected was going to continue, drawing this line out, you can see the dotted lines for transistors and clock speed. What happened was we still got more transistors, right? The number of transistors continued. That is to say, this is Moore's law, and Moore's law has not yet ended. It has to end eventually, but has not yet ended. However, what did end was scaling of clock speed. And this is referred to as Dennard scaling. And Dennard scaling has simply run out of steam for a variety of reasons. And I'm not going to go into those here. But in short, the chips are basically too hot or they leak too much voltage. So it's not really possible to clock these things up in any realistic way. So things were great in the 80s. If you needed to speed up your program, you just didn't do anything. You could literally just go and have a beach vacation and wait, and your code would run faster by virtue of the fact that time had elapsed and computers had gotten faster. But today you have to work. Today it's really hard. And so the only opportunity Homer has for a duff is going to be in the form of an energy drink at this point. So I'm going to explain right now why performance has gotten so complicated and why we're going to have to do new things to get us out of these problems that we've in some way created for ourselves. So here is the way a typical performance evaluation goes, where somebody says, I have an idea, like Homer has an idea, I'm going to speed up a program. So Homer goes and rewrites some code, changes around some things, maybe refactors some stuff out, and eventually ends up with an optimized version. At least he hopes it's going to be optimized. So he goes and he runs the programs. There's A, the original program, and A prime, the optimized version. A takes 90 seconds. Great. A prime takes 87.5 seconds. So Homer says, woot, 2.8% faster. All right. So his genius idea to optimize the code was successful, or so it seems. So it is faster. And the question is why? Why is it faster? So of course, just a total accident. So what could have happened was this interaction between the changes that Homer made and the underlying hardware. So there's a lovely paper that a few of my colleagues wrote back in 2009. The paper has a wonderful title, Producing Wrong Data Without Doing Anything Obviously Wrong. And it gathered together a bunch of information showing that very modest changes, things that you would never expect would have a big impact, can actually have a gigantic impact on performance. And so things like changing the link order, that is to say, if you have a make file and you have a bunch of .os, if you move those .os around, that changes where the functions end up in memory. Likewise, if you change the environment variables actually are loaded into memory when you load your program, and then the stack starts after it, so it moves the program stack, which means that data has moved around, right? So you might think, well, okay, these are fine. These seem like they shouldn't have any effect, but it turns out they can have a gigantic effect. They can have an effect that is larger than the impact of no optimization to full optimization, which is you can get plus or minus 40% swings. So let me explain what's going on. Here's an example. So suppose in the original program A, before Homer made his changes, there's two hot lines of code, and they both map to the same cache set. So modern hardware, especially because things have run out of steam, they've gotten quite complex in an effort to extract every bit of performance out. And so there are these on-chip caches. The caches are organized into sets, and they're not like, they don't necessarily take full advantage of the whole size of the cache. And if you have a bunch of things that map to the set, it can overflow it, and you get a result called a conflict. which means that the cache is no longer efficient and you have to go fetch information from memory, which is slow. However, when Homer made his changes and made his optimized version, it could have been the case that just by sheer accident, he ended up making it so that things that used to map to the same set no longer do. And there's something that's either cold or there's just nothing there at all, resulting in no conflict. So going from a conflict to no conflict could mean that your program is faster simply because of the cache. So you might think, well, this is maybe the only issue to deal with, but it turns out the cache is not the only thing to blame. There are lots of performance-sensitive microarchitectural features on modern chips that are influenced by program addresses or data addresses. These include a branch predictor, which tries to predict whether, which way a branch is going to go, like is it the if condition or the else condition. That's based on tables that are indexed by program counter location. There's a thing called a TLB, which maps your virtual addresses to physical addresses. And if you have something that used to fit in the TLB, which is a kind of cache, and now because you've moved things around, things straddle pages and they no longer fit in TLB, that can seriously degrade performance, or vice versa. You could make things accidentally fit and then things get better. There's a thing called a branch target predictor. There's a prefetcher. Suffice it to say that there's lots of stuff going on and it's quite complicated. All right. In addition, optimizations themselves over time have kind of run out of steam. Even so, if you factor out all of these layout changes, it turns out that across a vast array of these applications that people use to test compilers, the speedups that you get that are statistically significant are really quite small. So you really can't count on much assistance from the compiler to really get you out of this problem. All right, so performance is really brittle. If you change something, you can get dramatic swings in performance, and the performance swings that you get are really vastly larger than the compiler can even produce. So Homer needs help. Homer can't rely on compiler optimizations anymore, can't rely on computers getting faster every year, and unfortunately, tools have not kept up. So let me show you an example of where tools fail for Homer. So suppose Homer is in modern day 2020 and has an idea for an app. And Homer's idea for the app is this great idea because it involves cats and the internet. So the idea is you go on your smartphone and you take a picture of a cat, and then it gets sent to some servers and it comes back and it returns all the images that match this cat in the form of memes. So this is great. Clearly, it's going to take over the internet. He has a great idea for the name. He's going to call it Ogle. And Homer is convinced it's going to totally disrupt image search. So he goes and sets about building Ogle. Here's the way the prototype is going to work. You take a picture. It sends it to the Ogle servers. And in Homer's genius move, it saves the image in the database so it can be retrieved later by other Ogle users. It then goes and finds similar images and sends the results back. So if we step back a minute, I'm just going to describe the software architecture of this of Ogle. In a sense, when you go to Ogle, it's going to create two separate threads, one of which is going to go and do some compression of the image, maybe shrink it down in size to a thumbnail or something. It's going to save it to a 3.5-inch floppy disk, as servers do. And at the same time, in parallel, it can actually be extracting the features that it's going to use to look up these other images, then perform the search, and then send them back to the user. And of course, this is the whole process, and they sync at the end. So I've simplified things a lot, not just in the form of putting these in icons, but also we're talking about concurrency. Concurrency involves these things like locks to prevent things from happening simultaneously and clobbering each other. So real applications obviously are more complex. Fine. Let's say Homer goes and produces this application, ships it, everybody loves Ogle, but then Ogle ends up being really slow. So this is really sad. Homer is sad. What is Homer to do? So what Homer would normally do, what any of us normally in principle should do, is go use a software profiler. So a software profiler essentially goes and takes your program and produces statistics about it, and those are meant to inform you as to what you should do to make the program run faster. So the big ideas in software profilers really came out in the 80s and 90s. And this is a bit of a caricature, but to a first approximation, this is what profilers do. They do something like report the number of calls that you make to each function, and they report the runtime for each function. So you get these statistics, and what you're supposed to do with them nominally is you find the code that is frequently executed and that runs for a long time, and that's the code where you should spend your time, right? That's what you optimize, and that's going to make your program run faster. So the question is, when we do this in Ogle, is this actually going to help? Would this speed up Ogle? So suppose Homer takes the profiler, gets the information, finds the code that lasts the longest, that runs the most time, and he applies it to Ogle. And after a lot of effort, it turns out, oh no, what he did was he optimized the loading blinky part. And so that's not really helping Ogle go any faster. But what he did was he found frequently executed code. That loading thing is quite frequently executed, and it runs for a long time. In fact, it runs for the longest time. It runs from the beginning to the end of the whole Ogle process. So optimizing that is clearly a mistake. That's not what he should have been optimizing, right? And it turns out that existing profilers just don't do a great job of finding the important code in modern applications. In modern applications, we care about things like latency. We have programs that run forever conceptually. They're parallel, they're asynchronous, they're concurrent. And the existing profilers just have not kept up. They're essentially still stuck back in the 80s. So we need to do better. So the question is, what would speed up Ogle, right? So we would like to know, ideally, imagine there was some sort of magic pixie dust that we could sprinkle over the Ogle source code, and it would land on the code where Homer needed to spend his optimization efforts, right? So suppose it was this magnifying glass, that is to say the search part, that would be great. I would tell Homer, go work on this. It's guaranteed to produce a certain result. So what would this information look like? So it's maybe not going to look like sparkles on your source code. That might not be as helpful as you'd want. So what we propose is something we call a causal profile. So a causal profile tells you where your optimizations will make a difference and tells you how much of a difference they'll make. So suppose you've got these components of your program, and you've got a graph. On the x-axis, you've got the speed up. That is the speed up for an individual component. And on the y-axis, you've got the program speed up, or the improvement in throughput, or the reduction in latency. And we'll talk more about that in a minute. The kind of graph that you'd like to see is, look, if I spend a lot of time on the search part, I'm going to get a bang for my buck that's pretty high up until a certain point when it plateaus. So I'll know to optimize, and I'll know when it's time to stop my optimization efforts. Similarly, I'll find code where I shouldn't spend any time, right? It turns out this compression thing maybe is never going to be a bottleneck no matter how fast I make it. So this is really useful to know. I'm not going to work on that at all. And I might find other code, like the indexing part, feature extraction, where, yes, I don't get as big a bang for my buck as with the search, but if I keep working on it, I'll make the program run faster and faster, right? So this is great. It tells you, really, if I speed up a particular component by a certain amount, I will get a certain speed up, and so I can plan my effort accordingly. So this is all terrific. It would be wonderful to have. The challenge is, how do we get this information? So what I want to know is how I do a certain change, right? I get this effect. So I'm going to describe something that's impossible first, and then show you how to make it possible. So the impossible part is we're going to run experiments, and we call these performance experiments. So these experiments depend on magic. So if we could magically speed up every component, we could speed it up and then observe what the effect is, right? So we speed it up by a little bit, and we get a certain speed up. We speed it up a little more, we observe another speed up, right? And so on, right? And then we just do this for every component. We see, well, if I sped that up, that has no effect, and so on, right? And then we can use this to build our graph. Unfortunately, we're going to have to do this without magic, because magic is not a thing. Also, if we had magic, this is what we would do. We would magically optimize the things to 0, and it would be awesome. But magic doesn't exist. Sorry, Homer. So we need another way. So how can we do these performance experiments without magic? So the key insight that causal profiling depends on is using something that we call virtual speedups. So a virtual speedup is kind of like a theory of relativity thing. What we're going to do is we're going to give the effect of speeding something up by slowing everything else down that's running concurrently with it. So here, when we go and we speed up virtually the transmission, what we're really doing is we're slowing other things down. It turns out it's really easy to slow things down. It's just harder to speed them up. So when we slow those things down, we can then observe the resulting slowdown. And that slowdown corresponds to the speed up, the results we would have gotten had we actually sped that thing up. So we get a point in our causal graph, and we can just rinse and repeat. We do this over and over again. We observe the results, and we build out the graph. And we'll do this for component by component, just as described before. So here we observe the effects. And eventually, we get all the results for the red one. And finally, we do the same for everything. All right, so there's our causal profile. So this is great. Now, I've spoken about this in terms of program speedup, but this doesn't necessarily make sense in the context of a program that is not meant to ever end. And the Ogle server conceptually runs forever, and making the Ogle server terminate quickly is not a goal, right? That's not what we want. So what we actually care about is we care about things like how long does it take between sending a request to Ogle and getting a response back? And this is referred to as latency, right? So the other thing we might care about is how fast did the results come back? How quickly are these things being served up? And this is called throughput. So when you're doing causal profiling, you don't just run causal profiling with an ordinary program without any changes. You have to make some slight annotations to the program. We call these annotations progress point. So progress points. So for example, suppose Homer wants the throughput to be higher for sending responses back. So to optimize this, Homer has to mark it as a progress point. And in our implementation, this is just a macro. And so the way this works is every single time the code runs, it registers this fact, and it keeps a counter, and it runs the experiments and tries to accelerate the rate at which those things are occurring, or it observes the impact on those things. And so when you have the real server that's deployed, it's doing this for all of them simultaneously. And this one progress point that you put in measures throughput and gives you a graph where the y-axis is throughput. So that's with one progress point, right? So it says if I speed up some component, how much faster will I get that particular thing to run? However, what if Homer wants to minimize response time? That is the time between starting a request to Ogle, like saying, here's my kitty cat, until you get the pictures back. So here, you have to add two different kinds of progress points. We call them latency progress points. There's a begin and an end. And the way it works internally is that this begin and end just keeps track of the number of things going through the system, and it also keeps track of their rate. And it turns out that we can exploit this this classical result from the field of queuing theory called Little's Law. And the way that Little's Law works, we've reordered it a little bit, but it turns out that you can actually get latency just by keeping track of the number of transactions in the system and the throughput. And we can measure the throughput by using the existing progress point functionality that I described before on one of these progress points. Great. So we built a causal profiler for Linux. It's called Cause. And it ships with Debian and Ubuntu. It's quite easy to install. So on Linux, as long as you have super user privileges, you can install it. And then you run it just by saying cause run -- and your program and the arguments. And then it initializes it. It starts running these random performance experiments on code that's running and observes the effect. Again, you put in your progress points, and then it'll produce results that either are about latency or about throughput. So I'm going to show you some case studies of using causal profiling on Ogle. So we didn't really build Ogle, but we have the components that could make up an Ogle. So one is the compression part. It's called Dedup. Another is image comparison that actually allows you to do this business of looking up images and finding similar ones. And of course, hooking it up with a database like SQLite. So let me talk to you first about Ferret. So here's what happened when we ran Ferret with causal profiling, where we wanted the throughput to be higher. And what we discovered was that you can see that there's a couple places where there's a substantial bang for the buck. especially on the top one. And it turned out that all of these things were in separate components of Ferret. So the top one is in ranking, the middle indexing, the bottom is segmentation. And Ferret is organized as a pipeline. And so these are the colors that came from the previous graph. And you can see it starts with input, and it sends everything through and then produces output. And the way that Ferret is built is that it assigns a fixed number of threads to every stage. But we now know that certain stages, speeding them up can have a big impact. And some, like feature extraction, don't matter that much at all. So they probably don't need as many threads. So what we did, probably one of the simplest optimizations we've ever done, all we did is we reorganized the number of threads that were assigned to things based on the predicted speedup. And in fact, we got a 21% speedup just by reorganizing which threads go where. So this is not something that would show up in a normal profile at all. And so this was really great. We were able to get this very, very quick speedup with minimal effort. So one of the cool things is we're also able to validate that Cause really was doing what we hoped it would do. So for example, if we focus in on the ranking part, we increased it from 16 threads to 22 threads. This is a 27% increase in the amount of resources devoted to ranking, which should lead to a 27% increase in ranking throughput. And if you look at the graph, a 27% increase in ranking throughput leads to a 21% improvement according to Cause's predictions, which was exactly what we observed. So that's great. Cause is doing what it's supposed to do, and it's guiding us to optimizations that would basically have been impossible to find otherwise. I'll walk you through one other one real quick because it's a lot of fun. So we looked next at dedup. Dedup does compression by deduplication, hence the name. And the way it works is really simple, in conceptually simple, I should say. You take a picture, and you've got another picture, which is quite similar. We're going to compress how much space is stored for these pictures by carving out the elements that are definitely the same and the ones that are separate, and then splitting every image instead of being one object into a pointer to multiple objects that are their components. So the first image is Grumpy Cat 1, and it's these three pieces. And the second is Fun is Awful, and it has those other pieces, and the shared component only occupies the memory that the one image takes up instead of being duplicated. Great. So the way that dedup works is that there's a hash table. The hash table has some hash function that it applies to the images, and then it has buckets, and it stores them in not the image itself, but a pointer to it into these various buckets. All right. So in theory, these things should be spread out pretty uniformly across all of the hash table, right? So you should have pieces here and pieces there. It turns out that Cause actually noticed that there was a problem in the hash table. And so we were surprised by this. And we thought maybe the issue was that there was one big lock that was causing contention, but it turned out that was not the issue. So in fact, there are many, many locks, crazy number of locks. So then we were like, wonder what's going on. So Cause specifically said that the loop that accesses this list is important. And we've now ruled out anything having to do with locks. But in principle, we said, well, maybe there's just not enough hash buckets. And so it's leading to a lot of collisions. So we increased the number of hash buckets. And this led to no performance improvement whatsoever. So really, the question that we ended up with was what else on Earth could possibly be causing collisions? So we took a look at the hash function. And it turns out that the hash function was a catastrophe. So the hash function, this graph shows for all the buckets, so we had made it 1,024 buckets, how many items ended up in each bucket. And you can see that there's a ton that end up in a very small number of buckets. So the overall utilization was just 2%. That is, all of the things binned, they hashed to just 2% of the bins, which is really no good. It turns out that the hash function, first, you shouldn't roll your own hash functions in general, unless you're very careful. Whoever wrote this used a plus sign to combine the values in the images. And this actually leads to a normal distribution, which is not what you want. You want a uniform distribution. So by changing the plus sign to the XOR, which is the caret, we were able to get 82% bin utilization. So literally changing one character, we got a 9% speed up. And it turns out that, again, we were able to actually measure whether causes predictions were accurate. The blocks per bucket on average went from 76 to 2. This led to a 96% traversal speedup, and that, according to cause, would lead to 9% speedup, which is what we got. So we optimized other things. I don't have time to talk about these in this talk, but we optimized SQLite and sped it up by 25%, also via an optimization that would never have been revealed by any other kind of profiler. As I mentioned before, 9% on Dedup, 21% on Ferret. We've applied cause to a bunch of different things. We've gotten some substantial improvements with very, very small amount of programmer effort. So cause is quite effective at pointing us to exactly the lines of code that need to be changed. My favorite is probably the fluid animate and stream cluster, where the authors wrote their own custom barrier to synchronize a bunch of parallel threads. And this turned out to be a pretty poor implementation, or at least one that was not anywhere near as good as the system implementation. So we removed the custom one and used the system supplied one and got 38 or almost 70% speed up by deleting a line, in effect. So great. So that's cause. We've basically got effective performance profiling now that is good for modern applications. And it's easy to install and use. And if you have any performance issues that you're interested in dealing with that are in C or C++ or Rust or Java, then this is where cause shines. So like I mentioned, this is great for your applications written in these metal languages, in the not so metal language of Java, in the maybe scary for metal language called Rust. So these are fine. These are all great languages, but he ran away because of the Rust. So anyway, what about going back to these languages like the slow languages I mentioned before, like Python? So I got a little run in there, right? So Python is still a problem. Why is Python a problem? So Python is a problem because it is, as I mentioned, really fat and slow. But Python is an unusual language. In the sense that, well, there's many senses in which Python is an unusual language, but in particular, Python is really deeply embedded in an ecosystem, which is written in C. And this means that it can really be used as kind of a glue language to take your Python code that just glues together a bunch of components that are written in C, that is to say, in metal languages. And to the extent that you can do this, this will speed up your Python programs a lot, because really the Python code won't be spending very much time running and just sort of orchestrating things in these metal languages, which, as we know, are going to be vastly faster. So to this end, we've built a profiling system that we call Scalene, and Scalene is designed to help Python programmers move their code from bloated, slow Python into fast and efficient metal languages like C, with basically just telling them which parts of their code need to be moved into metal land, if you will. So Scalene is quite easy to use. If you're writing you've got your Python program, instead of invoking it with Python, you invoke it with Scalene. There's a number of options. You can tell it I only want to profile CPU. I would like HTML output. You can get a list of all of these options by typing --help. So I'm going to walk through a simple little program. This is a program that was sent to us, and it turns out that this program, we were able to quickly identify a problem by using Scalene and speed it up quite a bit. So it's nice and small and fits on a slide. So I'll show you what Scalene produces. So when you run Scalene on this code, you get a lot of information, and so I'm going to walk you through what it's telling you. First, it shows the amount of CPU time that's being spent, but unlike a normal profiler that just says, here's where I spent CPU time, Scalene divides it up into the time spent in Python and the time spent in native code, where native means the metal. It also indicates how much time is spent in the system, and the system means I/O, for example. And that's another thing that you might want to be able to, like, you want that information to know what you can optimize and what you cannot. You can't optimize CPU performance if the bottleneck is not the CPU. Next, it shows how much memory is being consumed, how much of it is from Python. So is it Python that's allocating memory, or is it the native code? and where is it coming from. So you can see the line 6 says 763 megabytes are produced by this one line of code, and it's not Python. So 0% is not shown on the screen. It means that it's definitely not Python allocating the memory. It also has this handy dandy little graph that it creates. This is inspired by sparklines from Tufte. The idea is that you basically can see it as a graph over time. So the x-axis, if you will, is showing you time, and the y-axis is showing memory consumption. At the top, you can see the memory consumption over the lifetime of the program. And on the bottom, on line 6, it's the 87% that is just for the program on that line of code. And then finally, it has this new metric that we call copy volume. And this is an important metric because copying is what happens when you go between Python and native code, or C, and when those results come back. And if you do that too often, that itself can be a bottleneck. So you have to be careful about how much stuff you do. It's best if you sort of get all the stuff in native land, the stuff runs in native side, and then comes back instead of constantly going back and forth. So in sum, you can see that for this particular line of code is clearly problematic. It's spending 34% of the total runtime in native code. 763 megabytes are being allocated. 87% of the total memory activity is happening on this one line of code. And it's exhibiting this sawtooth pattern, which turns out to be a very clear indicator that copying is happening. And this really clinches it. It says there's just a ton of copying happening. So what's happening is, by accident, the programmer put in this call np.array, which is meant to convert the input from whatever it is, like a Python array, into a NumPy array, which is much, much smaller and more dense. It's the metal representation. But it turns out this was already a NumPy array. NumPy's uniform random number generator already creates NumPy arrays. So what it was doing was allocating an array to copy it into, copying the old array, and then deallocating that array. So that's the sawtooth bump. That peak is when it allocated a new space to hold the copy in addition to the space that was necessary for the original, and then it deallocated it. So this turns out to be easy to fix as well. All we do is we get rid of the np.array call. So now, instead of saying np.array of this thing, we just remove it. That is, in fact, semantically identical. And you can see this has a big impact. Suddenly, the CPU percent has dropped a lot. The memory usage continues to be substantial. It's 85%, but it is over a smaller denominator. And that sawtooth pattern has gone away. You can see that it went from 1 gigabyte to 860 megabytes in total memory usage. And the runtime also dropped from 6.3 seconds to 5.4 seconds. So in sum, Scalene gives you these benefits. It is precise. It has all this information, but it's not just precise. If you have a profiler that's really precise, but it's dead slow, nobody will want to use it, right? Your whole thing is you've got a program that's too slow. And so if you take a profiler and it slows it down even further, that's just going to be painful. So Scalene also is fast. This graph shows a bunch of previous profilers, and on the far right, you can see Scalene in its CPU-only mode or its full mode, which does the memory profiling and copy volume profiling and everything. And you can see that Scalene imposes pretty limited overhead. So 1.0 would be perfect. So 1.1, 1.3 means 10% or 30%. Some of these existing profilers, including Profile, which is a standard profiler that ships with Python, slows down program by 16x, and others are like almost 10x or 35x, which is crazy. It's important to note that these things only indicate percentage of time spent in a particular line of code at best. They don't break it down by which ones are Python, which ones are C. And most importantly, they don't have any of the other information about memory. So there's only one other memory profiler that we were aware of, and it slows things down by a factor of 152x. So on this one program that took 5 seconds to run, running it with a profiler took 12 minutes and 38 seconds, which is crazy. And we've seen cases where the memory profiler slows things down by 1,000x. So scaling is a huge win over the CPU profilers in terms of their precision, and memory profilers simply because they're incredibly slow. So you might be asking yourself, how on earth do we do this? And basically the theme of scaling is to find weird like aspects of these irrational exuberance languages and leverage them. So what we do in all of these cases is find things that they're doing that seem to be limitations, and then exploit them or work around them in some way that allows us to get more information out than seemed to have been possible. So I'm just going to talk about one of these today. It's quite easy to understand, and it's nice and clean. So most of these scripting languages, in fact, all of them now, have this phenomenon that's called deferred signal delivery. So like some previous profilers, scaling is a sampling-based profiler, which means it periodically interrupts the Python program and checks where it is at that moment, and it does this over and over and over again. This allows it to operate with low overhead while getting pretty precise information. So this is fine if you have code that's running exclusively in Python. So if you send a signal every 0.1 seconds, for example, it will get delivered roughly every 0.1 seconds, as you would hope. However, Python itself actually doesn't just deliver the signals that come from your timer. It delays them until Python regains control. So if you execute some code that actually runs in C++ or C, like NumPy, none of those signals get delivered until that code finishes executing. So this is unfortunate because from the perspective of a profiler, nothing has happened. Basically, there'll be no information gathered, and it could be the bulk of the time that your program is actually executing, and it'll get no information. And worse, it'll mislead you. So you could have a program, and the program says, oh, I'm spending all my time in this stuff, whereas secretly you're actually spending your time in native code that's not even going to show up in a report. So this is really bad. This seems like a huge problem. But we kind of turned lemons into lemonade here. And so here is what we do. Every single time we get a signal, we record the current time. That is, what is the time on the wall? And when we come back and we get a signal again, we compare and see how much time has elapsed. Now, if we're not interrupted, then it would be whatever the delay was, the actual interval of 0.1 seconds, for example. However, there could be a delay. And if there is a delay, we know that that delay is basically because it was executing native code. So then we can account for it. So we keep these separate counters. We have a Python time counter and a C time counter. The Python time counter, we only increment by the actual sampling interval, and we attribute the rest of the delay to the C time. Likewise, we can actually leverage the fact that we can measure this thing called virtual time, which is the amount of time that we have in fact spent running on the CPU, and discover how much time the process spent in system time. That is to say, doing I/O or sleeping for some other reason. So this, by basically, we have this deferred signal delivery, which seems to be a problem. By leveraging it using these other timers, we're actually able to recover a lot of information. So it turns out this is quite accurate. Here is just to show you that it's accurate. We've got a little program that we've designed to run for a certain amount of time. We actually measured how much time the C takes, and we have a sleep, which puts the thing to sleep for some period of time. Oh, actually, in this particular case, I'm misspeaking. We have C code, which actually invokes a C method. So it's not about sleeping, it's about native code. And then Python code, where it's running in the interpreter. And so you can see that in principle, the Python code, which is shown here, should take 30% of the time, and the native code should take 70% of the time. And in fact, it comes up with nearly exactly 70-30. The error is about 1%. So scaling does a really good job using these techniques. We hope to extend scaling to some other irrational exuberance languages. Basically, all of these languages have features that are in common. And by using these features, we should be able to actually get the same kind of results that we get for scaling and apply them to these languages without too much difficulty. We're currently looking at doing this for PHP, and colleagues of ours at Northeastern are looking into applying it for the R programming language. So to conclude, Scalene is this profiler that's designed for handling these non-metal languages and making it easier for you to optimize not only the Python parts, but really steer you to identifying the parts that are in Python and should be turned into native code by splitting out the native time and the native memory from the results, very precisely indicating exactly where memory is being consumed, and in particular where copying is happening, which indicates a problem of moving stuff across these boundaries. It's fast, it's easy to install and use. If you use pip on Python, you can just say pip install -big U scalene, and that will do it. So in sum, scalene should help programmers out there who are stuck using Python. Don't get me wrong, I like Python. It's a fine language as long as it's not choking you. Making your Python programs run faster. And if you're using metal languages and modern applications, then you should use Cause. Also quite easy to install. And here are the links to the various GitHub repositories. And with that, I will conclude, and I'm happy to take questions.
So thanks very much for that enlightening talk, Emery. I think we've got a ton of questions that have come in over the duration of your talk. I'm going to try to sort of hit some of the high-level ones so that we can kind of get a broad picture of what people are thinking about as it relates to your talk. I'm going to start with something that kind of goes back to one of the first set of slides that you talked about, this distinction between metal languages and irrational exuberance languages. And I think the impetus for this question is that people came up with these irrational exuberance languages for a reason, which is that they're much easier to program in than metal languages. Yeah. So how do you balance programmer productivity that you get from languages like Python and Ruby and stuff like that with the performance that you kind of have to go to C or C++ to get?
Yeah, so I mean, that's a great observation. I mean, I think that the irrational exuberance part was that performance no longer mattered. I used to hear that articulated all the time. Computers are just getting faster and faster. It's not a problem. Don't spend all your time on this. We can focus exclusively on productivity. And I think these languages are great for productivity, but they can also be really, really slow. And if you spend any time using Python, that's the one of those languages I spent the most time with, you quickly run into performance issues. Sometimes it's great, and then when it's not great, it's terrible. So I don't think that because Python has all these great libraries that are written in native code, it's not necessarily a huge tension. You can write your program in Python, and if you use something like scalene, you find your bottleneck. If your bottleneck turns out to be something for which there's an existing C library, perfect. It told you essentially what to do. Ideally, we actually would like to extend this research to essentially tell you, here is the library you should be using. Right? Like, we have identified certain characteristics of your code. Those happen to be satisfied by some kind of library. Here is the library recommendation that you should use. I mean, in an ideal world, we'd also just automatically apply the library, but that might be a bridge too far.
Yeah, that would be an amazing tool to have access to as a programmer who works in these irrational exuberance languages. We had several questions that came in that I think were kind of related to the same general issue, which is uncertainty in measurement. So both in terms of when I'm doing this kind of profiling, do you worry about the profiler perturbing the results that you get? But also just more generally, the programs that you're profiling might have a lot of uncertainty or variability or non-determinism that you have to deal with. So how do you manage that when you're building these kinds of tools?
Right, that's a great question. So first, both Cause and Scalene are built on sampling. So sampling really means that you have very little impact from the profiler itself. So the profiler is only waking up very periodically and doing some sort of thing. With Cause, we were very careful to make sure that whatever it did was not biased. That is to say, it didn't have an effect one way or the other on the reported results. With Scalene, we couldn't play the same tricks because you're doing stuff at a Python level. But again, it's sampling based, so it should wash out. Variability, there's definitely inherent variability and noise in lots of programs, and not just in the systems that they actually execute on. And this is something that complicates reasoning about performance, period. I mean, it's important to actually understand how much variance you have If you get a result where it's like, well, this thing is spending 3% of its time, and every time you run your program, it's plus or minus 3%, then you should consider that to not be within kind of a confidence interval. So interestingly, we actually have this information for scaling. I just haven't come up with a way of displaying it. So we have confidence intervals that we build internally, and we just don't show anything where the confidence is too low. Visualizing that is tricky. There's already a lot of information coming up. So the way we've chosen to do it is just to not report things where the confidence is low, that this is not just due to the kind of variance you would get. And I think that's probably a reasonable way forwards on these things, is just to have profilers that decline to report things as being actionable if they're likely to be noise.
Makes sense. So we have a couple of questions that I think tie together two things that might actually also give you an opportunity to talk about some of your other research, which is, you mentioned the finding of Mitkovich et al. that like really small differences can kind of swamp the effects of even O3. And you're using tools like scaling and cause to make performance improvements to code, or to make changes to code that you hope will lead to performance improvements. How do you know that you're not just hitting the same kinds of weird hardware effects when you, for example, change the number of threads in Ferret?
Yeah. That's a great question. So, so cause in particular actually turns out to, by design, have an effect where it's sort of immune to this problem. So the reason is that if you have a multi-threaded program and you're randomly interrupting it, so you're randomly picking things that are happening and you're randomly doing different sizes and different everything is unbiased, and you're in effect getting different executions every time because of the concurrency. So you're, intuitively, you're mixing things up constantly. So the whatever code is running on the processor, whatever memory is currently being accessed, those things are changing all the time. So that actually has the effect of giving you kind of a random, what should I call it? It's sort of like an electron cloud, in a sense, of the distribution of everything. And so when you get points over time, it kind of factors out all of those effects. So it's a great question, and it's spot on. So we had a paper where we also built the system, and I didn't talk about it today for lack of time, but the results that we have for -02 and -03, I mentioned, you might have gone, might not have noticed, that I factored out the effects of memory layout. So we built this tool called Stabilizer, which does this by actually randomizing everything at runtime. So in a weird way, so Stabilizer does it precisely. It does it for sequential program. It has a random placement of functions, random placement of the heap, random placement of globals, random placement of the stack, and it does it over and over again. What happens with cause is that you kind of get the benefit of that just by virtue of the fact that you're running concurrent code. So the concurrent code is causing this kind of disruption, whereas Stabilizer is going to work for a sequential program as well. Hope that answers the question.
Thanks. Yeah, that's a great answer. Yeah, no, I think it's the concern is a real one, and I think you've given a good reason why we might be able to sort of accommodate it. There's a few questions that are kind of related to something that I thought was interesting. It's something I hadn't even thought about until these questions came in, about the interaction between cause and existing compiler optimizations. Are there kind of weird interactions that happen? Like if you turn on compiler optimizations, will cause either give you an incorrect diagnosis of where an issue might be coming from, or does it sort of affect what looks like the important parts of code? And then somebody asked a slightly different question, which is, could you use something like cause to help target compiler optimizations?
So let's see. So, I mean, cause is really about identifying, you've got a program and you want to know what parts of it you should speed up, right? If you are going to apply cause, you should definitely apply cause with the optimized code that you'd be running in production. It doesn't make sense to run cause with unoptimized code. It just, in a sense, it's like you're performing an experiment on a pig, and you really want to see if the experiment applies to trees. It's just like, don't do that, right? Like, you really want to run the experiment on the thing that you actually care about. So with respect to compiler optimizations, I mean, I don't think, so there's the layout stuff, and compilers actually do take into account layout and try to do layout optimizations with mixed effects. And like I mentioned, these things are super brittle. So just the mere fact that, you come in and your username is Homer and somebody else's username is Arun, it differs by one character. That one character is going to shift the stack, and it can have a gigantic impact, right? So I feel like that the effort that's spent on layout optimizations, people should be careful, because unless you're running the same code all the time with very similar kind of size data, you'll get very different effects. So I'm not sure that Cause has anything to say in particular about where compiler optimizers should work, unless it's one of those situations like, boy, if I spend an hour in the compiler, like imagine the compiler could just go to town for an hour or a day optimizing some code, and they just don't do it because nobody wants their compiler to be so slow. If you were willing to say, look, this code really matters to me, I'll be gone this weekend, you go optimize as much as you can, and I'll come back, like that actually would be fine. Like I think many people would be happy with an optimizer where you could be like, I know you normally are trying to be nice and friendly to me, but you go crazy and spend, a day, 2 days, a week running. That would be interesting.
Thanks. So I think we have time for one last quick question, and I'm choosing this one because I think it'll give you an opportunity to talk about yet another one of your cool pieces of work that's related. Somebody heard your discussion of stabilizer and asked, does the randomized placement of things you've mentioned have any implications for security?
Right, yes. So yes. So actually, when we wrote stabilizer, we were trying to decide whether we should pitch it as a performance thing, which is what it was intended for, or a security thing, or both. And we decided that for cleanliness of discussion, we would just focus on the one thing, so we kept it as performance. But actually, re-randomization and so on, the amount of randomization stabilizer produces is really, really high, and it's one of the first, it's definitely the first system out there to randomize things at runtime. And so many of these things at runtime. So there's a whole line of these things that are called moving target defenses. And so moving target defenses are exactly intended to thwart certain kinds of attacks. The Die Harder paper that Milind mentioned in the beginning is about a randomizing memory allocator specifically designed for security. So we have random allocation of things in space. There's guard pages. You can't predict any more than you can predict a random number generator. Its output, you can't predict what addresses things will be at. And so the likelihood of an attacker being able to safely exploit something where they have addresses or known offsets basically goes to zero. So yes, it definitely, lots of security implications for randomization.
Thanks for that answer, Emery, and thanks for all of your answers and for talking about your amazing work and a lot of the other pieces of work that you've done. But I'm afraid we've run out of time for today, and I'd like to thank Emery again for his informative presentation and his answers to all of the questions. And I'd like to also especially thank all of you for both asking these great questions and for attending the talk and participating. So one set of questions that we got that I didn't really get a chance to answer is that, yes, this talk was recorded and will be available online in a few days at learning.acm.org. And you can find announcements about upcoming talks and other ACM activities at both learning.acm.org and at acm.org. Please do remember to fill out our quick survey where you can suggest future topics or speakers, and you should be seeing that on your screen shortly. On behalf of the ACM, Emery Berger, and myself, Milind Kulkarni, thanks again for joining us, and I hope you'll join us again in the future. And with that, we'll conclude.